Katie DeVore and Mike Forte to the group. Will this go? There we go. Okay, so a bunch of coastal folks already on the line. I think you don't need a whole lot of motivation for satellite remote sensing. Our existing survey methods, whether it's LiDAR or boat-based GPS surveys or RTK walked shorelines, drone surveys, any of these things are time-consuming, expensive, and then we have a lot of hazardous areas that we can't really reach across our district sites. And so this sort of results in oftentimes sparse data, both in space and time. So this then leads to the lack of sort of data-driven management decisions. So we're hoping that this new approach sort of enables this new data source that's low cost, sort of low commitment, and quite frequent. And so you've probably heard a fair amount now about trying to understand better the now state of our coastline from General Graham. And so this is important whether we're trying to determine what areas were most impacted by a storm, or whether we're managing a beach project, such as a nourishment or a berm, or a dredged area. So again, this can provide us that now state of our coastline. Just to sort of orient you with our sort of project history and overall objectives, this technology is relatively new, so we first needed to evaluate the accuracy at a sort of a range of sites. So that was the first phase of the work. And in doing that, we wanted to see specific examples of how it could be used for management applications. And then finally, the goal is to create a more user-friendly ARC tool for district use. Right now, it resides within Python, so it takes some level of coding expertise. So we wanted to make this a much more approachable tool for districts. Just briefly on the methodology, this algorithm leverages the Google Earth Engine to ingest imagery from the 3 Landsat satellite missions, as well as Sentinel-2. These range in resolution from 10 to 30 meters. The great part of using all these different missions is we have revisit rates of between 5 and 16 days. So it's an immense amount of data. Of course, some of these images might have clouds, so we have to go through and filter those out. We've added some more automated QA/QC approaches to the existing algorithm, but then it uses the modified normalized difference water index to classify the image into sand, white water, and water. And then from there, it uses this thresholding method to actually extract the shoreline along a set of transects. And so what you have then at the end is a time series of shoreline shapefiles shown by this image. We then use the tide and the time of the image was taken to correct for the tide and shift our shapefiles accordingly. So again, the first phase of the work focused on evaluating the accuracy of this algorithm. In the past, this has grown in popularity really over the past couple of years, but most folks have just sort of assessed the accuracy on a transect by transect basis. So we wanted to take this a step further and look in the longshore as well. We did learn that it's pretty difficult to track down robust sort of ground truth data. And so we talked with a lot of different districts. So we were looking for areas that were maybe problematic to manage or had a specific project. But the priority was having a data set to compare to. So here are the sites that we ended up choosing that we ran for 2 decades in time. And the orange text is just describing the nature of the ground truth data itself. So it's anything from 407 profiles here at Duck to just 11 profile shorelines, for example, in the New Jersey area. So we were happy to encompass the West Coast, East Coast, Gulf Coast, and then we also have this Great Lakes site as well. So So this was really a pretty fair sized wrench that was thrown at us in the sort of later stage of last year, I guess. We were having we noticed a lot of variability in sort of the skill of this, and we started to plot then by the satellite mission. And so you can see these plots here to the right are just colored. So the y-axis is the relative shoreline position, x-axis is time, and then the points are colored by the different satellite missions. The top one, you can see that these missions align quite well, and our reference shorelines are in the black. However, if you look at these bottom two panels, we started to notice randomly these large offsets between missions, which was a pretty big problem. Luckily, at this sort of similar time we discovered this, the creator Killian Voss in Australia, he noticed the same thing. His initial efforts again were focused on that transect level, but once he started to scale up in the longshore, he noticed some similar behavior, so he was able to correct for this. And so we sort of backtracked and took the newer version of CoastSat to implement into our ARC tool that we'll talk a little bit more about later. So if we discard the sites that have this issue, unfortunately, it was a fair amount of them. They're starred here on this plot, but this is a summary of our accuracies for all sites. So on the y-axis, we have our offset from the ground truth, or that's the mean horizontal difference from our ground truth. And then we have our sites across the x-axis. So a few things to take away from this. Quite a range in variability and accuracy. So that mean horizontal error ranges anywhere from about 4 meters up to over 20 meters at some sites. And some of these sites even happen to be adjacent to one another. So we were hoping to dive in and try to figure out sort of what's driving some of this variability. Overall, we were happy with the overall mean here of 11.3 meters. This is consistent relatively with other work that's been done around the world. And we also found a slight 3.5 meter onshore bias. We did some comparisons based on satellite, and sort of as expected, Sentinel-2 that has the best resolution of 10 meters. The Landsat missions are corrected to be 10 meters, but we did expect this to have the best accuracy, and it's better on the order of about 2 meters compared to our Landsat missions. Shannon looked a lot at trying to improve our image co-registration. There's some software packages out there. We first looked at Aero6. That proved to be pretty challenging to implement into the workflow, computationally expensive, and just a little buggy. So we shifted gears and started to use ArcPy. We tested this at a couple sites. The takeaway here is it does, it does sort of tighten up your data, and we were able to detrend that standard deviation from about 1 to 3 meters at this Wrightsville Beach site. However, if you take that then and see how it improves your shoreline accuracy, at Duck, for example, it only improved our overall accuracy by about 6 centimeters. So again, those mission-to-mission offsets, like I showed before, are probably a stronger influence. This is something that the sort of the broader community, I think, is trying to address as well. But right now, it seems like it's only a minor contribution in terms of error improvement. A great aspect of CoastSat is it's also capable of extracting a slope in the event that you don't have any ground truth data, or maybe you're at a very remote site that you've never been to. So if you can run CoastSat for at least 10 years, we found that it's reasonably reliable in terms of generating its slopes. We did have some discrepancies, as we've highlighted here. Really gently sloping Benson Beach of an error. So that's good, right? So we can, ideally you would have some field-based slopes, but this is advantageous for, using this approach where we don't have field measurements. So that was sort of the summary of the instantaneous comparisons. And a big or major piece of this is looking at sort of historic and decadal trends. And so the Landsat missions stretch all the way back to 1984. So again, it's this very powerful sort of data set, both in space and time. And what we found is the decadal trends are even better than instantaneous comparisons. They agree quite well with the ground truth. The more time you have, the better your accuracy. For example, this plot showing with 200 days of data, your mean difference from the ground truth trend is about 3 meters per year. But after you hit that nearly 2-year mark, your mean difference shrinks to about 4 centimeters per year. So this is basically saying that, with this amount of data, we can sift through the noise and produce reliable trends with a free satellite data source. So yes, we're going to switch gears. Shannon's going to talk about some of our efforts with PlanetScope.
All right, thanks, Ian. So in addition to traditional CoastSat, which uses Landsat and Sentinel images, we were looking at using some high resolution imagery from PlanetScope. So CoastSat PlanetScope uses imagery from Planet satellite, and that has a resolution of 3.5 meters and 10-meter image resolution from Landsat and Sentinel-2. So using Landsat and Sentinel, we have about 1 shoreline a week, which is good for long-term change, like Ian just talked a lot about. But with CoastSat PlanetScope, we can get a shoreline a day, and with that high resolution imagery and that higher temporal density, it allows us to use this imagery to enable storm response and smaller management project monitoring. So we were really looking to see what kind of accuracy shorelines we can get from CoastSat PlanetScope and test it at a couple sites across the US. This is a commercially available product instead of a publicly available one, so we pay for each image that we download. So we wanted to be really intentional with the images that we downloaded, so spreading out the different types of environments along the US East Coast and West Coast, and also really honing in on some projects to see if we can apply this imagery to our use-case projects. So each of these sites were picked for a specific reason. So I'll start off on the East Coast. We picked Harvey Cedars, New Jersey. There was a near-shore berm placement, and we wanted to monitor that site, see if the sand came on shore and occluded the shoreline. We have Duck, which has a lot of validation data, so we could really get a sense for the accuracy of the shorelines we get from CoastSat PlanetScope. And also, we're impacted by storms over the span of our data set, so we can really see what type of storm response we can use CoastSat PlanetScope for. In California, we worked with Scripps to pick 2 sites out there that they have a fair amount of ground truth for. In Encinitas, that's a pretty narrow beach with a cliff back. So we really wanted to see if the location of the shoreline position is coincident with the cliff erosion events that are happening over there. In Ponto, there is not sand, it's a cobble beach, so we really wanted to test the CoastSat PlanetScope algorithm to really push it to its limits and see how robust it is. So we retrained the classifier there and tried to see if this was a feasible thing for sites that are not just sandy beaches. In Sunset Beach, Hawaii, we picked that site because there was a large erosion event, and it's a high tourism, high economic value place. So it was really an interesting erosion event where there was low significant wave height and a long period. So they didn't expect it to be such an erosion event that it was, and a couple homes fell in the ocean. So they were really trying to glean some insight of that event as well. So when you run CoastSat PlanetScope, you get an output that looks like this. This is cycling through all of the shorelines that came from the duck imagery that we have. The first panel is the RGB image that you download from PlanetScope. And then the image in the middle is the classified image that Ian mentioned before, the sand, water, white water, and other land features image. And then there's the last panel there is a near infrared minus blue band image. So that really helps the algorithm pick out the shoreline, and we can then tidally correct those shorelines and look at them in a time series cross-shore space. So here I'm showing all of the CoastSat PlanetScope shorelines in red, and those are tidally corrected. In green, we are showing the 97 lug surveys that we have during that time, so that's our ground truth data. You can compare those two data sets, so 430 CoastSat PlanetScope shoreline, a root mean square error of 4.5 meters that had a very slight landward bias and a 12-meter standard deviation, and that standard deviation is a proxy for noise of those shorelines. We also compared the lug shorelines to the traditional CoastSat, and during this time period we had 387 CoastSat shorelines. When you compare that to the lug shorelines, you get a root mean square difference of about 8.5 meters and a 40-centimeter landward bias. The standard deviation of the CoastSat shorelines was about 12.5 meters, so it's a slightly noisier data set and had about double the root mean square error that the CoastSat PlanetScope had. So we were excited about these statistics, seeing that we can have a more accurate shoreline when we use the high resolution imagery. In contrast, we can look at Harvey Cedars, New Jersey. This is the berm placement that I mentioned before. So on the left map there, it's just going to orient you to where we are on the coast. There are some groins in this site, so that does impact the shoreline extraction method and also creates those embayments. But in the blue dots in that white square, that's where the berm was placed. In the top right, I'm showing you those same cycles of the shorelines that CoastSat PlanetScope derived for us. And then in the middle portion of the study site, I pulled out one of these transects, transect 4, and you can see that the nearshore berm was placed right where that yellow arrow is. And after that berm was placed, you can see the shoreline accreted and then it's stabilized. So you can see that this project really did impact the beach system and it did grow the beach, and so that's always good to know. It is interesting, just an interesting thing to note is that they didn't have any ground truth shorelines during the time period I'm showing here. The last ground truth shoreline they had before the placement was in 2018, and then they didn't survey the beach until later in 2022. So these satellite shorelines really do paint a picture of what happened at this project when we didn't have ground truth in situ data. So really is good to have these. Okay, so we can zoom into a storm event that happened in our duck site. So this is a nor'easter that happened March 4th, 2018, and just around where that black box is, highlighting in that time series. During the storm, there was quite a bit of overwash, and it's an image right in the bottom right of the overwash that happened during the nor'easter. Our ground truth data in green, the lighter green is the pre-storm survey, that's February 26th, and then we had our post-storm survey on March 15th. And then when you show our PlanetScope shorelines nearest to our lug surveys, we have the pre-storm survey in February 2nd and our post-storm shoreline on March 27th. And it really did capture this erosion that happened in the middle portion of the property. And that's a scale of 30 to 40 meters of erosion. And then when you zoom up to the north and the south, you can see that those shorelines do converge. So it does capture the hotspot of erosion that happens on the property. In addition to PlanetScope imagery, we're looking at Maxar imagery. So Maxar imagery is WorldView 1, 2, and 3, and GeoEye. And this is even higher resolution than PlanetScope. It has a 1.8 meter ground sampling distance. An example of WorldView 2 image is shown on the right there. And what's great about this Maxar imagery is that it is free to districts with justification. So we could really lean in on this data source that we already have access to. One thing to note is that they need to be tasked, so it's not just collecting as it passes over every site. So that also leads to this inconsistency of the temporal density that we have. As you can see, Benson Beach, Washington has only 3 images for the same amount of time that Sunset Beach did. So just something that we can look into in the future and could improve the accuracy even more.
Awesome. Thanks, Shannon. All right, now we're going to jump over just a few screen grabs from our tool and just some description. So again, we're migrating this from its sort of Python home into what you can see here is an ARC tool. So we've added Mike Forte recently for some of his ARC expertise. We're working on our documentation. And then stay tuned, of course, for a training webinar later this summer. But just a quick overview of our tool. It's meant to be simple. Site name, you would draw your polygon of interest, or maybe you already have a polygon of interest, and then you are going to enter your time interval, start and end date, what sort of shoreline contour you're interested in extracting. We've been operating at 0. Here's where you would put your field-based slope, or leave this blank to have CoastSat generate it for you. This is just showing you which tidal gauge it's picking, and then you also have the option to adjust your transect spacing depending on sort of whatever research question you're trying to address. And so then we hit run, and sometime later it's going to download all your imagery and run through the shoreline extraction process, and then eventually populate your map project with this time series of shorelines colored by time. So this is just an example from our Great Lakes site.
Can I ask a question?
Sure.
Yeah, so this is a good example, I think, for folks in the field. It has a pretty short enough duration for shoreline change. How big is the data set file once it's run through? And do you store anything other than just the output?
We do store all the imagery. Associated CSVs. So it can be a pretty hefty chunk of data, right? Depending on your time interval and I guess your site, right? If you're in a fair weather place, you're going to have more data, less clouds, right? But yeah, this is sort of the current desktop tool, and I'll mention sort of our next goal after that. Something to add?
No, I would just say, yeah, the imagery is probably the largest storage limiter that you would have, and once you run the tool and get the shorelines, you could easily delete the imagery that it downloads from Google Earth Engine until you want to run the tool again.
Mm-hmm.
So
I guess I'm just asking, is it going to be like in the hundreds of megabytes range or tens of gigabytes? Like what scale are we talking for something like this, like a year?
Definitely not hundreds. Shannon's looking at we'll circle back to this. We should know. She's looking for an example.
Okay. Yeah, you can do it later. Okay, that's
fine. And so this is for you district folks, this is a place to pay particular attention to. I've just added some of these additional plots. So I mentioned analysis products. Our goal, is the primary goal is to provide you with the shoreline time series, right, and shape files. But we want to go some steps further. And so here are some of our ideas so far is just, creating some of these trend plots shown at the bottom through time, colored by satellite mission with a moving average line through it, just so you can sort of, this helps my eye at least, sift through some of this noise. That's a longer term trend example. And then in the top right is another piece of the tool, just a time stack generator. These are a little bit more complex to digest, but I think in some cases they're pretty useful. This one, for example, was from the Harvey Cedars site that Shannon showed. The dashed lines represent sort of the time of the placement. And then the solid vertical black lines represent the placement bounds. So what you can see is at the onset of that placement within this area, we can see those darker blues start to emerge sort of adjacent to that placement site. So those are some of the products we're thinking of thus far, but again, we're hoping to lean on the district users ultimately. An example of how this can be applied, we've teamed up with the Detroit district. We wanted to, we're operating primarily at sort of a project by project site, but we wanted to test the scalability of this tool as well. And so we were maybe a little ambitious, but we've been mapping the entirety of the Lake Ontario shoreline. So this is about 700 miles of shoreline. We've broken it up into these tiles that you can see in white along the shoreline edges. And this is part of their Great Lakes Coastal Resiliency Study, and they're planning to couple this with their water level information to try to understand the relationships of water level and shoreline behavior. Or so done with this. This is it's taken a while, but we're making good progress. So then, just to wrap up, again, we're pretty excited by our accuracy assessment. Again, sort of as expected, relative to other work around the world, we have an overall mean horizontal difference from the ground truth of 11.3 meters. That does range across our sites. We've learned that we can use the CoastSat generated slopes, and that the decadal trends agree quite well with ground truth. And again, I think we've emphasized, the potential uses here for project monitoring and design. We can test how, our projected decay rates compare to the real sort of project. Etc. So we've learned that these approaches are pretty complex, and a lot of other researchers across the globe really have encountered sort of similar issues. And so I think collaboration with a newer technology like this is very crucial. And again, stay tuned for that training webinar. And just a couple more slides before we finish up. Switching gears once again, but this is thanks to Kate and Spicer for providing this slide here. So we've talked about this ARC desktop tool that we're getting close to releasing, but I think sort of the longer term end goal would be to develop sort of a broader national scale near real-time web-based tool that you could use similar, in your project, but you could also navigate to a little bit easier without relying on ArcGIS. So this slide is just summarizing part of the comprehensive water risk management SFA, or strategic focus area. And within that CWRM SFA, there is a work package called the Open Coast Physical Processes. And one focus of that is to develop national scale integrated observation capabilities. So that's sort of how we see this fitting in down the road, where the satellites, as you can see here on the left, would provide sort of that high level understanding of your coastal condition, maybe an initial storm response gauge, and then from there, you could determine where you might need to actually go out, boots on the ground, and start to survey, and add some fidelity to your measurements. That fidelity could be added through, UAS or robotics. We could add wave buoys, or use surface vessels to collect sort of the different environmental conditions. And you could even go as far as adding, core cam stations to your site. But again, this satellite piece is sort of a critical component to identifying the now state of your coastline. And just looking at some other, web tools that are out there already. The Australians have been leading the charge, and here's just an example. They've teamed up with the USGS, and you can see in the top left here is their web viewer that shows the average shoreline. A larger vision to Spicerbach or Cape Brody, but just wanted to add that in sort of as this work unit wraps up, we're thinking about sort of bigger picture ideas as well. So with that, we will quit talking at you and hopefully open up the floor to any input or questions. These are just meant to sort of guide the discussion. Again, the analysis products are important. We also, are trying to determine what sort of time scales you're interested in. Are you most interested in those storm impacts, project equilibration, or maybe more historical trends? There might be some Maxar users out there. Anyway, happy to take any questions.